Okay, everyone, and welcome back. In this lecture, we're going to talk about this other way of trying to come up with models that we'll call ensemble models. In this first video for today, I'm going to recap this decision tree concept we talked about on Monday, as well as talking about a few extra things that we want to talk about for decision trees. Namely, how we can use them to make predictions of probability about the outcome, as well as how we can prevent overfitting. So those are kind of our two big goals for this video. So just to kind of remind you of where we are right now in the quarter, so far in the first 2 weeks, we talked about regression, namely kind of how to do regression to learn a line or curve of best fit. We talked about how if you use a curve that's too complex, that you could potentially suffer from overfitting, and then how to prevent overfitting by using something like regularization, namely ridge or lasso, to help prevent your model from actually overfitting. And then the last 2 weeks, we've been discussing classification, and we started with kind of ideas and high-level concepts in classification, as well as one particular model, logistic regression. Last week, we talked about other factors other than accuracy that we care about, like bias and fairness, and how models, if we're not careful, can perpetuate injustice. And then this week, we're talking about other types of models, namely naive Bayes, decision trees, and today, ensemble models. Different methods to achieve classification results. Now, it's important to highlight that we're talking about different methods, and how they relate to this idea of fairness usually depends a lot on context. So we can't always say a ton about context-specific matters, but it's a useful framework to think about that all of the things we talked about last week with fairness and bias apply here as well when thinking about decision trees, naive Bayes, or ensemble methods. But usually the focus is on the context you're applying them to, which might be very, very different from application to application. So what I want to quickly think about is this idea of this ML pipeline that we introduced before. From training data to feature extraction to an ML algorithm or quality metric and an ML model. I think it's really, really important whenever we learn something new, even if I don't explicitly show you this picture, to try to help you think about where is what we're learning and how does this fit into this ML pipeline. So a decision tree fits squarely in the ML model. It's a different type of model that we're going to be using. It's this kind of flowchart model. The quality metric we used is an old one. It's classification error, trying to minimize classification error. Training data and feature extraction, same things as before. And last time we spent a lot of time talking about an algorithm to learn a decision tree, which would fit in the ML algorithm. And so I think it's always useful to go back to this picture to make sure that you understand kind of how this new concept relates to previous ones. And this framework is a useful one for thinking about that. So as a reminder, when we introduced decision trees, we talked about this idea of a flowchart or a decision chart. We have branches and leaf nodes that help us make decisions. The branches tell us, ask us questions about features and tell us to go certain directions based off the particular values. So for this decision tree about credit loans, you might have a branch about credit, and the credit might take on the values excellent, fair, and poor. And we might use that to then make decisions later down the line. So you might have a split based on credit to separate all the training data based on excellent, fair, or poor credit. And then if you only wanted to have a one-level tree or a decision stump, you would just make each of those kind of branches from there a leaf node and make the value of the leaf node, the prediction if you ever make it there, the majority class, in that case, safe, and risky. Now, there's nothing that necessarily needs to stop you at one split. You could potentially do more. And we talked about one way of stopping is if you reach zero classification error. But this idea of a decision tree is generally or pretty universal regardless of how tall you allow it to be. We also talked about methods of trying to find the best split or an algorithm to do this, trying all possible features, finding which one minimizes classification error. We also talked about what you might want to do if you have a feature that takes on numeric values. In particular, we want to find the best threshold to split the data into based on some numeric feature. So to pick some value and separate the data in less than or greater than. The reason for this as a reminder is that we can't have a split for every possible value we might see, since with real numbers or integers, there's an infinite number of values that it can take on. So instead, we choose a threshold and make our decision branch less than or greater than or equal to, or however you want to define that. So we need to find some threshold to separate our data. And we talked about that the best way of doing that is to try every possible midpoint between the data, which requires sorting the data and then trying thresholds that are in between all of the points. And that can get us to kind of trying every kind of useful threshold. So this is just a procedure for choosing a split for one numeric feature. But we still have to do this process of try every feature. If it's numeric, we need to run this algorithm as well. And this will help us find the optimal tree. And we keep doing this repeatedly and repeatedly until we reach zero classification error. Okay. So what I want to introduce that's new from before is the notion that decision trees can help us make predictions about probabilities. Namely, that if you want the tree to output, I think there's a 75% chance that this thing is actually a positive label, we're able to do that. Nothing fundamentally needs to change about the decision tree. All we do is just keep track of a little bit of extra information, where the leaf nodes don't just track the majority class, but they keep track of these counts. How many of the data points that ended up here were the majority, and how many weren't. Something like excellent having 9 safe and 2 risky, or fair having 6 safe and 9 risky, or poor having 3 safe and 1 risky. We just keep track of both counts. We'll still know that which one is the majority, but you keep track of both counts. So then when a new client comes in and they say, oh, what's the probability that giving them a loan is safe? Well, this is the probability that Y is safe. Whoops, didn't mean to zoom in. This is the probability that Y is safe, given whatever their input features say. And instead of just reporting the probability is 1 because we're going to predict that it's safe, there might be uncertainty in the world if we have some data that isn't perfectly separated here. If we have 3 safe and 1 risky here and we never did any further splits. Well, in that case, what we could use is we can use that kind of that count data to help us make a prediction about, or a statement about how certain we are. What we'll do is if we're trying to predict the probability it's safe, we'll just take the count of safe and divide it by all the data points that end up at that node. So there are 3 safe data points and 3 plus 1 total data points, which means a probability prediction of 0.75. It's, again, very similar to this idea of predicting a majority class, but now we just report, if we want to report a probability for this prediction, it's just the proportion of data points at this node that belong to the majority class. So 3 divided by 3 plus 1. To think about this visually, we can think about the decision boundary for this tree, but we can think about coloring in its predictions as not just the label +1 or -1, but actually the probability or how confident it is. And if it's very confident, meaning that the result is very clearly one direction versus another, this probability should be closer to 1. And the way this would happen is if most of the points that end up for that node end up being part of that majority class. So here in this just tiny toy data set, we learned some split on feature x1 being less than negative 0.07. One thing to note is, it's a bit annoying about these pictures, is the labels, and I had to get this from another source, the labels put the negative class first and then the positive class. So when it says 13.3, it's saying 13 negative, 3 positive. I know it's annoying because I used positive on the left before, but this is a picture. I wasn't able to edit it very well, unfortunately. So here we have 13 negative answers and 3 positive. So we want to ask what's the probability of a negative prediction for any point in here, like this point. We would report the number of negatives divided by the total number of points on that side. And you can see there's about 3 positive points and 13 negative points on that side. So we report 13/16. So again, just like how we predict the label being the majority class, you also can predict the probability being the proportion of the data points that belong to that class. So it's a useful extension. As you have more and more splits, you can imagine that the probabilities change, where if you have a subset of the data in one leaf node that's pure, meaning that it's all of one class, the probability of belonging to that class will be 1 because there's no examples that aren't in that class. Whereas where it's a bit muddier, where there's more of mixing, then you have a probability closer to 0.5. And so you can have these decision boundaries like before, but also color in their confidences, how high that probability is on a scale from 0 to 1, in the case of just measuring what's the probability of it being the positive class. And you can imagine, as you have a deeper and deeper tree, each leaf node then has fewer and fewer points, potentially making it so that all of the points in that leaf node have the same class. Then the probabilities go closer and closer to 1 or 0. So it has this kind of overconfidence thing, just like with logistic regression. And speaking of logistic regression, I think it's useful to think about how the decision boundaries differ between decision trees and logistic regression, where logistic regression is learning this line. And as you increase more features or a higher degree polynomial, you can learn more and more complex functions. Just like with that, increasing the height of your tree will make it a more complex series of these kind of dividing lines. So just like with logistic regression, we can learn more and more complex things, but do note the types of decision boundaries learned in decision trees look different than logistic regression, where decision trees are learning these like vertical or horizontal cuts to the data because its decisions are based on less than or equal to, in the case of real valued features. So this then kind of leads us to our next point, which is, if I'm going to keep growing this tree, it's going to potentially start overfitting. How can I stop that? So overfitting happens in decision trees quite easily when your stopping criteria is when you achieve 0 classification error. Because if you just keep splitting and splitting and splitting, you're going to be making split decisions on fewer and fewer points as you kind of get deeper and deeper into the tree. So while the decision boundaries are useful and interpretable, they're not stable if you have this really deep tree, because it might result from a high variance decision that you got this particular threshold because there was a lot of variance in these kind of small number of points deep in the tree. And so it's possible for a slight change in your data set to lead to a large change in the outcome because a tall tree is a high variance tree. So if you want to prevent overfitting, we have to slightly change our learning algorithm. Either we need to stop growing the tree at some point, which we call early stopping, or we need to prune the tree. Once we've grown out a full tree, cut off some of the branches and some of the leaves to make it simpler. Now, I'm going to really focus on early stopping and talking about ways of thinking about that. That doesn't make pruning not useful. It's just generally this early stopping approach is more commonly used, stopping the tree from growing to be too tall. And we'll talk about some notions of how to do this early stopping. So some stopping rules that we talked about before was that if you reach 0 classification error, meaning that all of the points in some node had the same class, so that the majority class of those data points got 100% accuracy. Or we had nothing left to split on. There's no other interesting information to split up the data. What we could do instead is modify this rule to include stopping conditions or early stopping conditions. And there are many, many ways that you can imagine implementing this. One is to choose a height of the tree or a maximum depth of the tree, saying, hey, I'm only going to consider trees of up to height 5. Don't let it grow any taller than 5. So this is one example of a way of doing early stopping, is fix how tall your tree can be. And you would this is just a hyperparameter for your decision tree model, which means you would choose it usually using something like cross-validation or a validation set. There's also notions of don't split if there's not a sufficient decrease in error. What I mean by that is if your split only is going to decrease the error by like 1%, then potentially you might want to say it's okay to stop. This might not always work. It might be something you need to tune as a hyperparameter, but is another way that people might think of overfitting, is that if there's not sufficient gains there. Additionally, another common one, similar to the max height, is a way of specifying what's the minimum number of examples that need to be in a leaf node before you split it. What I mean by that is if you have 5 data points in a leaf node and you set the minimum number of points in a leaf node to be 10, what that means is you're not allowed to split nodes. You're not allowed to create new branches as long as you don't have more than 10 examples. So if you set this equal to 10, example, min leaf data equals 10, that means any node that has fewer than 10 examples in it may not be split. And this is a way of preventing overfitting because you're not going to let it split on very, very small data sets. Now, again, just like with the height, the way you set this is with some kind of hyperparameter tuning with validation set or cross-validation. Also, don't trust me on the name of this parameter. I don't remember it off the top of my head. But scikit-learn has a way of specifying this. And just to note, this last one, the specifying the number of data points to allow a split, is the example hyperparameter tuning we're going to have you do on the next assignment. There's nothing necessarily wrong with max height, or there's no reason this is better. We just want you to work on this one. It's just it's a nice, a simple approach and one that they show in a lot of documentation. Okay. So this is kind of wraps up our discussion of decision trees. The decision trees are super simple. It's a very interpretable model that's understandable by people without too much ML experience. The algorithm to learn it and some details about it are a little complicated, but the high level, this idea of a flowchart, is not too complicated, and many non-ML experts can understand it quite well. And it's actually relatively efficient. I did describe how it does require lots of trial and error to find the right feature splits, but you can actually do this quite efficiently with most data sets. So people normally don't complain about slow decision tree training times. But most importantly, when you're training decision trees, it's very important that you control the depth of your tree with some hyperparameter. If it's too small, it's going to be too weak. It's going to not have enough capacity to learn anything interesting, meaning it will have high bias. If it's too tall, it might overfit your data, which might mean it might suffer from high variance. And even if you kind of are very careful and do a lot of cross-validation or use a validation set to find the most appropriate tree, they just tend to not always have the highest accuracy in practice. But this other things like efficiency and interpretability are really, really useful, and one reason why people might explore them.